Welcome to Chapter 4, Measures of Variability. I want to very shortly recap what we learned so far about how to describe data for one variable. In Chapter 1, we discussed why we conduct research. So we learned about asking a research question, how to formulate a hypothesis, how to determine the independent variable and the dependent variable, and also identify the level of measurement as nominal or ordinal or interval or ratio. After this part in the research cycle, we would go out and collect our data. So in Chapter 2, we talked about organizing the data once we have collected it. So we can, for example, organize the data in a frequency distribution table, in a cumulative distribution table, or we can display the frequencies in proportions or percentages. We also looked at how to display the data graphically. So, for example, we can do that in a bar graph, in a histogram, or in a polygon. And we looked at the shape of the distribution and were able to determine if our data were symmetrical or positively or negatively skewed. And then in Chapter 3, we looked at the measures of central tendency, the mean, the median, and the mode. With these measures, we said we can use a single number to describe what is average for or typical of a distribution. And while these are all very helpful, they tell us only part of the story. Because, for example, the measure of central tendency only tells us where the middle of the distribution is. Another way to tell us even more is selecting a single number that describes how much variation and how much diversity there is in the distribution. And these are the measures of variability. After this chapter, you will understand the purpose of measuring variability. You will know how to define a range and compute the range. Also, you'll understand the variance and the standard deviation. You'll be able to calculate the sum of squares, the variance, the standard deviation for both the sample and for the population. Let me give you a visual of what variability is. So, just to explain the concept. Let's say we are looking from the top down at a dinner party. And in the middle of the dinner party is where George Clooney is standing. And clearly everybody wants to be around Clooney at this party, right? He's the center. He's the mean of the party. Everybody wants to be around him. He's the average. And the yellow stars around him are all his bodyguards. The red dots here are a couple of his fans that made it to the party. And then the green ones are his close friends. So you can see that all of these, the fans, the bodyguards, and the close friends are all spread out around him at various distances. With the measures of variability, we can get one number that signifies how spread out each of these groups is from Clooney. So variability is defined as the quantitative distance measured based on the differences between scores. It describes the distance of the spread of the scores, or the distances of the score from the mean. And in this case, let's say our mean is Clooney, so how far are they all away from Clooney, the mean, right? By just one number. The purpose of measure of variability is to describe the distribution and to measure how well an individual score represents the entire distribution. Let me give you another visual example of variability. Here we have the population distribution of adult heights in inches. So if you look at this graph, you can see that we have the mean height is 70 inches. And of course, not everybody is 70 inches. So you can see we have people that are 76 inches. And we have people that are, very tall, 82 inches, and then we have 64 inches, and then fewer people on the very short end and fewer people at the very tall end. But the mean average is 70. So not many people are extremely short or tall, right? So height doesn't vary that much. So all of this, so 58 inches and 82 inches doesn't differ very much from the mean of 70 inches. So you can see that the graph is kind of skinny and tall because most of the values cluster around the 70, the average. Well, this is very different from when we look, for example, at weight, right? Weight differs a lot more. So there's a lot more variability when it comes to weight. So even so, the average weight in this case is 170 pounds, but it's very spread out. Many people are on the lower end of 110 and even lighter than that, or 230 and even heavier than that. So you can see that this graph looks very different. It's a lot more spread out, right? The data is farther away from the mean. So it's not that much clustered around the mean, and that's why we have a shorter and wider graph. So the measures of variability reveal the consistency or the similarity of the scores in the distribution. And it shows us how much the average score truly represents all the scores in the distribution. So here the average is 170, but there is really a wide spread in both directions going on. Versus the height, there's not that much spread. And the means and the standard deviation together provide extremely useful descriptive statistics for characterizing a distribution. So why is this important to know? Let me give you another visual example where I think the distinction becomes very clear why it is important. Variability measures help us to sum up a distribution of scores without really looking at each and every score. So if you can see here, for example, we have two different professors for two different classes, Professor Brown and Professor Yamato. And you can see that for both of the professors, the average grade in the class is a C+. Yet, if you look at the shapes, right, this is Professor Yamato, you can see the shape is very, very spread out. So in his class, people actually get grades all the way from A to F. And the average is a C+. If you look at Professor Brown's class, let's say it's a she, right, you can see that in her class, again, C+ is the average, but the distribution only goes from C minuses to B's, right? So there are no A's in her classes, no B pluses, because it stops right here. So the distribution is all very much clustered around the average of C+. So it's tall and short. Versus Professor Yamato's, again, it's very spread out, right, and not quite as tall. So measures of variability reveal how far from the typical or central score the distribution tends to vary. So just knowing that C+ is the average for both of those professors doesn't really tell you exactly what's going on in the data set. So if you know, for example, that in Professor Brown's class there is a very small standard deviation versus in Professor Yamato's class there is a large standard deviation, you know that in Professor Brown's class, with a small standard deviation, all of the scores are clustered around the C+. The basic measures of variability are the range, the variance, and the standard deviation. And we will look at each of these in detail and calculate examples for each of them. One way to describe how spread out the data set is by giving the range, which is just simply the difference between the highest, so the maximum, and the lowest, or the minimum score in your distribution. So the range is just the highest score minus the lowest score. All computer programs use this definition of the range, the upper real limit minus the lower real limit. While the range is helpful, it is often severely affected by extreme scores, and it might not tell us exactly what's going on when it comes to individual scores. So let's just look at this example of a basketball basket competition. So let's say we had a 5-minute competition. How many baskets can you make in 5 minutes? For the first group, we had the lowest as 15 baskets and the highest as 85 baskets. So the range is just the highest minus the lowest. So that is 70. But let's say we had another group. And in that group, the lowest was 30 in the 5 minutes, right? So in 5-minute competition, they did 30 baskets and the highest was 100. So the range here again is highest minus lowest, so 100 minus 30, and that's also 70. But clearly, if you just look at the two groups, you can see that while the range is exactly the same for both of them, the second group was a lot better when it comes to making basketball baskets, right? Huge difference between the first and the second one. So The range really doesn't tell us anything about the individual values in the data set. The most common and most important measures of variability is the variance and also the standard deviation. Both of these increase or decrease based on how closely the scores are clustered around the mean. So they both are measures of the standard or the average distance from the mean. The variance is the average of the squared deviations from the mean of the distribution, and it's a necessary companion concept to the standard deviation. So once you calculate the variance, it's really easy to get the standard deviation, but it's not the same concept. The standard deviation is just the square root of the variance and is the most common measure of variability. And both of them measure variability in interval ratio variables. First, let me explain the concept of deviation and variance in examples. In order to determine the deviation of a data set or the number that represents the distance of the scores from the mean, we need to find the sum of deviations to use as a basis of finding an average deviation. So to see how far each score is from the mean, we just have to subtract the mean from that score. The deviation score is the score minus the mean, and you do that for each score. So let's say we have the data set of 8, 1, 3, and 0. So let's say that's the data set for our population. We know for this formula we need the mean. We know the mean is just the sum of x over the total number of people. Well, the sum of x is just adding up all the x's. 1, 8, 1, 1, 1, 3, and the last person scored 0, so the sum of x is 12. We have 4 people. So 12 divided by 4 gives us a mean of 3. Now, according to the formula, we have to subtract the mean from each of the scores. So it's just x minus the mean. So 8 minus 3, 1 minus 3, 3 minus 3, and 0 minus 3. And we get 5, negative 2, 0, and negative 3. The problem is that if we sum this up, which means the sum of the deviation is always 0. Doesn't matter what your data set look like. The sum of the deviation is always 0. And if the sum is 0, then the mean deviation is also 0. And that doesn't help us to find the deviation. So we have to come up with something else. The way we solve this problem is by using the squared deviation. Because the problem with averaging the deviation scores that we just saw is that some have positive and some have negative values. And these always cancel each other out. The solution then is just to get rid of the positive and the negative signs. And the easiest way to do this is by squaring the values. Because remember, if you square a positive value, you'll always end up with a positive. But also if you square a negative value, you also end up with a positive value. And that solves our problem. First, we square each deviation score. And then we just sum the squared deviations. And that's what's called the sum of squares. So again, here's our data set. And now all we have to do is square each of these values. This is the squared deviations. And now we add up the squared deviations. And in this case, we get a sum of square of 38. And the variance, which you saw before we're going to need to get the standard deviation, is just the average squared distance from the mean. The variance is just the sum of squared that we just got over the number of people in your data set. You can see that there is a difference, not in calculations, just in the symbols. When we talk about the population variance, you see the Greek alphabet lower sigma. So it's sigma squared equals the sum of squared over the total number of people. That's the population variance. Since we squared the values, the variability is now measured in squared units. So in order to get it back into the original units, we just need to take the square root of it. So the standard deviation is just the square root of the variance. And you can see again for population standard deviation, it's just sigma now. And that's the square root of the sum of squares over n. For our previous example, this just means the square root of 38 divided by 4, which is 3.082. We looked at the logic behind finding the sum of squares. However, the definitional formula is very time-consuming and error-prone when we analyze real data. Because we first have to find each deviation score, then we have to square each deviation score, and then we have to sum up the squared deviation. So if you have a large data set, you can really make a lot of small errors. For this reason, we can also use the computational formula, which produces mathematically exactly the same results, but is often easier to use. So again, the definitional formula looks like this. The computational formula in comparison looks like this. And I'm going to give you an example of the differences when it comes to the calculations. For the computational formula, you can see that the sum of square is the sum of x squared minus the sum of x in parentheses squared over the number of people. So if you look at our original data set again, we had the scores of 8130, and you can see we only need two pieces of information really. That is the sum of x squared and the sum of x, and then square it. So first off, the sum of x is just adding the values together. So we know the sum of x is 12. We know the number of people, we just have 4 people in here, so all we need to get is the sum of x squared. That just means we have to square each of the values. So 8 squared, 1 squared, 3 squared, and then add them up to get the sum of x squared, which is 74. And these are really the only two pieces of information that we need in addition to the number of people. So plugging this into the formula, we get the sum of x squared, which is this value, the sum of x squared, so 74, minus the sum of x in parentheses, so that is 12, but then square it over the number of people, so that's 4. So again, we get the same sum of squares, because remember, it doesn't matter if you use the definitional or the computational formula, you have to get the same result. Again, it's 38, and you can see it's a lot easier than what we calculated previously. So most students really prefer the computational formula, because you can make a lot less errors in this one than the other one. Let's do a practice problem. For the following population of n equals 7 scores, start by computing the variance for the population. Please, at this point, pause the video and solve the problem. Always start by writing down what you know. So in this case, we know we have n equals 7, and we have the 7 scores, 8, 6, 5, 2, 6, 3, 5. We know for A, we are after the variance of the population. This is the formula that I will need. Here I can see I have n, but I need the sum of squares. So that is the next formula I'm going to need. So I write this formula down. Now I can see that I need the sum of x squared and the sum of x, because I have the number of people. So for this formula, I just need 2 components, and then I can solve for the sum of square. The sum of x is 35. The sum of x squared is 199. Now I just plug it in, and I get a sum of square of 24. Well, I know the number of people is 7, so now I use the population variance formula. So that's 24 divided by 7, so I get a variance of 3.43. To solve for B, computing the standard deviation for the population, I know I just have to take either the square root of the variance that I just calculated, or if I want to use the exact formula, I know the standard deviation, again, is the square root of the sum of square over n. So that would be the square root of 24 divided by 7, and that would be 1.85. So since we calculated the variance of 3.43 before, we could have just taken the square root of 3.43. Let's do another short learning check. Decide if each of the following statement is true or false. If you need to, you can pause the video at any time. Is this true or false? The computational and the definitional formula for the sum of squares sometimes give you different results. False, right? Because the computational formula is just an algebraic rearrangement of the definitional formula, so the results have to be identical. True or false? If all the scores in a data set are the same, the standard deviation is equal to 1. This is false. When all the scores are the same, they are all equal to the mean, right? They're all laying right on top of the mean. So their deviation then is 0. Let's do another learning check. What does the standard deviation measure? The answer is B. The standard deviation measures the standard distance of a score from the mean. When we look at standard deviation and variance for a sample and compare it to the standard deviation, the variance for a population, we have to discuss what the goal of inferential statistic is. What we want to do is draw general conclusions about a population, right? That's inferential statistic based on the data we have for a sample. The sample gives us very limited information, right? It's a small subset of the larger population, but based on that sample, we want to draw general conclusions about the larger population. But clearly the samples differ from the population, right? Because samples already, they are a lot smaller than the entire population. So if you have a sample of 100 from 10,000 people in population, clearly there is less variability in your sample than there would be in the entire population. So computing the variance and the standard deviation in the same way as for a population would give us a biased estimate of the actual population values. So if you look here, for example, at the population of adult heights, and let's say the top graph is the population distribution. And you can see the population variability goes all the way from here to over here. If we would select a sample from the population, because there are so many more people here, right? It's more likely that we're going to get people from here for our sample, right? Because there are just a lot more people in this bump here than there are already on the sides, because that's already fewer people. So most likely, most people are going to come in our sample from this distribution right here. So you can see that we are more likely to obtain individuals who are near the average in height, right? Because they're going to come from in here, and again, this is the average. And they're really less likely that we actually catch some very short people or some very tall people over here. So as a result, the scores in our sample will be less variable. They're going to be less spread out than the scores in the population. And it's for this reason that we need to adjust the formulas a little when we are talking about samples versus population. When we talk about the variance and standard deviation for the sample, we calculate the sum of squares just like we did it before. So exactly the same formula for the sample and for the population. However, the formula for the variance has an n-1 rather than just the n in the denominator. And the notation is a little bit different. So for the sample variance, we use the notation of S instead of. So for the sample standard deviation, we use the notation of S instead of sigma. So the variance of the sample then is S squared, which stands for variance. So the variance equals the sum of square over n-1, and the standard deviation of the sample is just S, which stands for the standard deviation, equals the square root of the sum of squared over n-1. Let's do another practice problem. So you have to always watch out for, are they talking about a sample or are they talking about a population? That's going to tell you what formula you have to use. So for the following sample, compute the variance and also the standard deviation. Again, first let's write down what we have. This is our data set. Then next, write down what is the answer to the question. In this case, start with compute the variance. So we know the sample variance formula is the sum of square over n-1, because we have to make that little correction. n-1, because we're talking about a sample. We know the sum of square is exactly the same formula as it was for the population. So again, we need the two components, the sum of x and the sum of x squared. The sum of x is 52. The sum of x squared, just squaring each value, adding them up, is 386. plug it into the formula, we get a sum of square of 48. Now we just plug it into the sample variance formula, so that's 48 divided by 8 minus 1, which is a variance of 6.857. We also need to compute the standard deviation, and again, either we just take the square root of the variance that we just calculated, or if we go according to the formula, we know the standard deviation of a sample is the square root of the sum of square over n minus 1. So we just plug in our 48 divided by 8 minus 1 and take the square root of that, and that is 2.62. In many statistical problems, we are required to determine the degree of freedom. The degree of freedom is the number of scores in a sample that are independent and free to vary. The formula for the degree of freedom, which will also be discussed further in future chapters, is just the number of people minus 1. So n minus 1. Let's do another practice problem. A sample of 4 scores has the sum of square of 24. What is the variance? We know that we have n equals 4, and we know that the sum of square is 24, and it's asking for the variance, so write down the variance formula, which is the sum of square over n minus 1. So now we just plug in the values, and you see that the result is 8. So C is the correct answer. For both populations and samples, it is easy to represent the mean and the standard deviation. The vertical line in the center denotes the location of the mean, and then a horizontal line to right, left, or both denotes the distance of one standard deviation. So here you can see the means are represented by the red lines and the standard deviations by the horizontal lines. So when we look at standard deviations in regards to descriptive statistic, we can see that a standard deviation describes the scores in terms of the distance from the mean. So we can describe an entire distribution with just two numbers, with the mean and the standard deviation. And reference to both allows a reconstruction of the measurement scale from just these two numbers. Also, you can see this in your figure 4.7 in the textbook. Remember from last time that the mean had certain characteristics. So when we did certain things, the mean behaved accordingly. So remember when we said we add a constant to each score. So for example, we added a +3 to each of the score, that the mean changed according to that. So the mean then changed +3 also. However, the standard deviation is unchanged, because if you think about it, the standard deviation gives us the distance from the mean. So if each of the scores change, for example, +3, then the standard deviation, then everything is shifted +3. So then the standard deviation is unchanged, right? Because the distance from the mean is exactly the same as it was before, because you shifted everything 3 over. This is different when you multiply each score by a constant. Remember again, the mean set is changed and the standard deviation is also changed. The way it is changed is that the standard deviation is multiplied by that constant also. Let's practice. After 3 points have been added to every score in a sample, the mean is found to be 83. The standard deviation is 8. What were the values for the mean and the standard deviation for the original sample? Please pause the video and solve this problem. We know that 3 points were added to each of the score. Well, we know that if we add constant to each of the score, the mean is also changed by that score. So if the mean is 83 now, and 3 points were added to each of the score, we know that the mean before was 83 minus 3, or 80. We also know that this does not change the standard deviation, right? Adding a constant to each of the score does not change the standard deviation. So the original score had a mean of 80 and a standard deviation of 8. Let's do another practice. After every score in a sample has been multiplied by 4, the mean is found to be 48 and the standard deviation is 12. What were the values for the mean and the standard deviation for the original sample? Please pause the video. So we are multiplying each score by a constant. That means that the mean is changed by that constant. We also know that the standard deviation is also changed, meaning the standard deviation is multiplied by that constant. So the mean is 48 divided by 4, which is 12. So the original score had an M of 12 and a standard deviation of 12 divided by 4, which is 3. Congratulations, you made it through another chapter. Remember, if you need any help at any point, just email me or see me in my virtual office hours. I will be happy to help you. See you in the next chapter.